Okay, well, thank you for coming. My name is Alvaro Menduina, and I work for the UK Civil Aviation Authority. And today I'm going to be talking about the assessment of risks to the space environment and its mitigations through structured judgment. Just a little bit of background about myself. I did a bachelor's in aerospace engineering in Madrid in the Polytechnic University. Then I moved to Delft to do a master's as well in aerospace engineering, which involved an internship at master thesis at Germany. I was working for OHB in Munich, and then I moved to the UK, where I did a PhD in astrophysics, looking into machine learning for the calibration of aberrations in telescopes. And for the last 2 years, I've been working as a mission safety analyst for the UK CAA, doing the assessment of licenses and spaceports in the UK, which is kind of the context of this presentation. And yeah, I'll be talking a bit more about that fairly soon. I don't really know the background of people in the audience, so I thought I might start with kind of an introduction to the space debris problem, but please stop me at any point if you think that you already know about these things, or the absolute opposite. If it's anything's unclear or you want some clarification, please let me know. I won't try to show the YouTube video. It's only 1 minute. I don't want to risk having more problems with Zoom. But the idea about the space debris problem is that throughout the space-related activities that we've been conducting over decades, a lot of objects have been left behind, usually rocket bodies from rocket launches, and also fragmentation events, things that collide with each other in space. So effectively, there's a kind of a cloud around the Earth orbiting that doesn't really serve any purpose. And usually these objects tend to stay up there for a long time, leading to potential collisions. And the problem with these collisions is that they only generate even more debris that then keeps on going and can cause other cascading collisions. So this is a problem that has been known for a while, but sadly, we haven't quite figured it out yet. The number of objects in orbit keeps increasing, both on the active side, so a spacecraft that we put in orbit, and also just inactive bodies, so things like rocket pods or defunct satellites that have completed their mission but are still orbiting. These can lead to very problematic events. So in 2009, there was probably the most famous collision in space debris history, which was the Iridium versus Cosmos collision. So these were two objects. Iridium was an active satellite from a constellation, and Cosmos was a rocket body left by the USSR that was effectively defunct. It was just orbiting without any control. And sadly, these objects actually had a close encounter and crashed into each other. And this created a debris cloud with thousands of fragments that will then kept orbiting and move towards other orbits. So this is a risk that we're very aware of, and it's increasing rapidly. But so far, we haven't done much to tackle this. And just to give another example of a really close call that happened actually a few months ago this year. So Leo Labs is a US company that has a network of radars, and they're tracking these objects. So they release information about close encounters between different objects and so on. And they showed this tweet that basically shows a very similar situation to what we saw between the Iridium and Cosmos a few years ago. And these two objects, so in this case, both were chunks of debris, just rocket bodies left over in orbit, which actually missed each other, but by a distance of like less than 6 meters, which is an incredibly close encounter. And had they collided, they would have caused like thousands upon thousands of space debris objects. So yeah, just as an introduction to the actual problem of space debris. Here I've just put together two plots to kind of show the situation in terms of numbers. So the one on the left kind of shows you the total number of objects in orbit, both actual spacecraft and just inactive objects from kind of the beginning of the space race up until like 1 decade ago, like 2013. So you can see that the numbers have been increasing steadily, and those big jumps are usually either collisions like they did in Cosmos 1 that we saw in 2019, or also anti-satellite tests that have been conducted. So in this case, there was a Chinese one that led to an increase, a big increase in the numbers. And then the one on the right is actually a simulation that shows kind of the long-term evolution of these objects in low Earth orbit, and it's taken from the European Space Agency annual report, and it shows two sort of scenarios or assumptions. The first one in red is just an extrapolation of the launch rate, so it's kind of assuming that we keep doing things as we're doing. How would the number of objects actually increase? And as you can see, it keeps increasing quite dramatically over the next 100 years or so. But perhaps more interestingly is the second assumption, which assumes that if we were to stop all launches at once, meaning that we don't launch any more satellites and we just leave the population of objects as it is, the total number of objects actually keeps increasing. And this is due to these sort of naturally occurring collisions between objects. So the problem is quite severe in the sense that even if we stop doing all these activities, the number would still increase, and this would lead to an increased risk in collision. So we're kind of at that crossroads of whether things are going to escalate even further, or whether we're going to take some action. And just to see and kind of highlight the importance of this, just put a piece of news highlighting that 2022 was actually a record year for space launches. And we actually average a rate of one rocket launch approximately every 2 days or so. So these things have been increasing dramatically over the last decade or so. Just to give you more information about the problem, but from the operational side of things and active satellites, BryceTech every year releases a report on small satellites and statistics about how many were launched and so on. So you can see how the trend has changed very severely over the last 10 years or so. Like in 2013, only a handful of small satellites were launched into orbit, and they were mostly related to like government and military operations. But ever since the sort of shift towards commercial operators and the arrival of newcomers like SpaceX and OneWeb, we have increased the pace at which we're launching satellites to the point that last year, more than 2,300 satellites were launched into orbit, which is probably more than the sum of like the last 8 years put together or something like that. So yeah, again, a really dramatic increase in the use of space resources and how many satellites we're putting in there, which will have implications onto the number of space debris and the number of collisions that we can expect. Moving on to kind of the introduction of the problem, the idea that we have in the CEA as a regulator is that in order to make sort of effective policy making around this problem of space debris, we first need to understand the risks. So we need to understand how severe the problem is, and also if we were to act on it and apply a certain mitigation, what would be the effect on the evolution of the environment. The problem with this is that usually this is a really complex process to model, and a lot of the inputs that we need for these simulations are incredibly uncertain. And I'm hoping that kind of the previous slide sort of highlights this problem. So just to give you a flavor for the different things that we are not too sure about, the object population itself, so how many things are up in there in orbit, is really uncertain. So we know about the things that we put up there in terms of satellites, but we also see that is changing rapidly. So the number of satellites that were launching at the moment was probably unexpected like 10 years ago or so. So it's really hard to include these predictions back into the models that may tell you about the orbital environment. But also the number of space debris objects is slightly unknown. So depending on the size, the tracking capabilities might not be good enough to know where these objects are. So for really small objects that are beyond our tracking capabilities, we're not entirely sure how many of those there are. So there's constantly collisions with spacecraft, between spacecraft and small pieces of debris that might not cause a catastrophic damage, but those are still there and they're causing a lot of problems. Again, the use of the space resources has changed quite significantly, not just in terms of the numbers of launches, but also types of missions. So over the last 5 years or so, constellations have sped up a lot, and there's many proposals to put a large amount of satellites in orbit. It's not very clear whether all these mega constellation projects will actually lead to a successful business. There's many filings and proposals, but it's unclear whether the actual business case will hold for most of them. So again, putting that into the predictions as to how many satellites will be in orbit is really challenging. Also, in terms of capabilities, this is something that could in principle like help with the problem. If we had better tracking networks, we could be more aware of like when these collisions or close encounters are going to happen. And there's also proposals and projects to develop autonomous collision avoidance, which is normally done manually by commanding the satellites to move away if the risk of collision is high enough. But there's plans in the future to do this autonomously by the satellites themselves. Also, something that I will talk later on, the levels of compliance of the disposal guidelines have changed a lot, and it's very unclear how these will evolve in the future. So there's a handful of disposal guidelines that tell operators to get rid of those satellites once the active mission is finished. But in the past, operators didn't really comply with these things, so the landscape has changed a lot. Commercial operators now doing constellations tend to be more mindful of these things, and they tend to remove the satellites as close as frequently as possible. But space is really challenging, and some satellites might fail and might end up just like staying up there. So it's really hard to predict how good these ones are going to comply. Also, the regulatory framework is changing a lot, and things like the geopolitical dimension of space also play a role. So the anti-satellite weapons testing and things like that. So I hope that provides a useful context as to why this can be challenging to model through conventional methods. And just to introduce kind of the goal of the study, here at the CA, we've been trying to apply structure expert judgment to tackle some of these questions, and at least characterize like what is the uncertainty that experts have on these inputs and their evolution, and try to use their knowledge to estimate how the risk to the orbital environment looks like and how the population of debris objects will evolve. Also, the notion of sustainability in the orbital domain is not particularly well defined. It's not as maybe as simple as in climate change, where you have a target for the increase in temperature globally, because the processes are so complex that it's really hard to understand what we mean by sustainability. So another goal of the study was to try and characterize what the experts themselves think sustainability means in this context, and also looking into how we can actually best tackle these problems. What would be the best mitigations to minimize the risk? I'll probably won't delve too much into the study, since you're probably very familiar with the methodology, but just to kind of give you a few details as to who we interviewed and so on. We have a cohort of experts across the space industry, so people who are either working here at the CA or work for companies across the space industry and are familiar with the modeling of space debris. In terms of the calibration questions, we kind of have a fairly decent source. The European Space Agency releases every year a report on the sort of the situation of the space debris environment, full of statistics that people kind of look forward to. So you can expect a lot of these experts to actually be fairly familiar with it, but it's quite a large report to the point that people are unlikely to remember all these things off the top of their head. So we found that that was a really good sort of data source for finding calibration questions. And then in terms of the questions of interest that we are keen to estimate, we divided them into three sort of categories for the study. The first one deals with like space object population. So instead of like focusing straight away on risk, we really want to understand what experts think the orbital environment is going to look like. So how many things we're going to put into orbit, because that has implications to things like collision risk and so on. Then kind of the core of the study would be the risk to the space environment, trying to characterize proxies for the level of risk, such as collision risk, and see how those might evolve. And then finally, we don't want to just like understand what the risk is, but we want to tackle it somehow. And this is kind of where consensus breaks up a bit, and we'll see that later on. But we thought it might be useful to include questions about effective mitigation measures, so try to understand what experts would do in order to tackle this problem. Just to give you an example of how the document looks like, space debris tends to be a fairly complex and nuanced phenomenon, I guess. So we need to add a lot of background information to the questions to make sure that the experts understand exactly what we are trying to estimate, and also to ground and homogenize the assumptions that they put into the questions. So yeah, there's a lot of like tailoring to be done to make sure that experts really understand what we're trying to achieve. And then we're also very keen on capturing the experts' rationale, because that gives us a bit of insight as to what the experts are really thinking. So kind of how the study has been sort of processing those expert rationale and trying to group them and get a bit of a sentiment interest when it comes to these questions. Moving on to the results, in principle, calibration questions are not the goal of the study. They're just a means to an end in terms of estimating the quantities. But as we started performing the study, we saw a lot of interesting results that were coming from the calibration questions. So in the context of compliance with mitigation guidelines, we asked experts how likely they think commercial operators have been complying in the past, so between the 2010 to 2020 decade. And the actual answer is there straight away from the ESA report at around 70% to 80%, so around 75%. This means that approximately three quarters of commercial operators were actually deorbiting their satellites at the end of life within the expected 25-year rule. And the answers that we got from experts, you see, are quite varied. And also they tend to be slightly pessimistic about compliance. The situation has changed a lot over the last few years. So if you see the following question, which deals specifically with constellations, but in the 2020 to 2030 decade, it improved from like 75% to well above like 95, but still, like, experts tend to feel that the compliance is actually lower than expected. So that was an interesting perception result. And one of the things that we also noticed was that for the last question, in that band of like light blue highlighted, most of the expert responses for that last question tended to be around that 75% mark, which actually aligns fairly well with what we had seen in the past. So there seems to be a lag in perception as to what the actual compliance is compared to previous years. Moving on to questions of interest. So looking into the space object population, we had two questions. One was, how many payloads do you think will be launched into LEO over the next 25 years or so? And this includes pretty much everything. So we just want to ask how many things are going to be launched in whatever context that is. And then the second question is a bit more of a snapshot, looking at how many payloads, if we were to look in 2050, would be orbiting the Earth as part of a constellation. And this pretty much dominates the population because constellations tend to include a large number of satellites. So by 2050, we can expect the population to be mostly driven by these constellations. You can see the logarithmic scale here in the plots to kind of highlight that experts had very diverse views about how many payloads were going to be launched, probably driven by the dramatic changes in traffic. So if the traffic had stayed more or less stable, you probably would have seen less of a discrepancy across people who are maybe more pessimistic about how many payloads are going to be launched and so on. And again, to highlight that this is important to us because this has implications as to the level of collision risks. Also interestingly, among the rationales that were given by people, kind of the most important was uncertainties about the feasibility of some of these mega constellations that have been proposed. You may also notice a bit of a slight trend increasing towards the expert numbers. You can see that they tend to give the latest experts, so 6, 7, 8, and so on, tend to have given like larger intervals and larger estimates for the satellites being launched. And just to highlight that this is actually driven by who works at regulatory agencies compared to industry. So the experts that are on the regulation side of things, a lot of my colleagues at the CEA tended to be a bit more pessimistic about these, the likelihood of these projects actually materializing. In terms of actual predictions, when we applied the equal weights decision maker to the data that we had, we arrived at a few estimates for the number of payloads being launched and also the number of payloads in a constellation. For the former, we had quite a wide interval, but something between several thousand to nearly 100,000 payloads being launched over the next 25 years. And then in terms of the objects in a constellation, we saw a median estimate of around 30,000 objects in constellations by 2050. And the bottom picture is taken from a conference presentation by the European Southern Observatory. So this is kind of the interagency body that deals with astronomy. And these people are very worried about mega constellations and their impact on astronomy, because these objects tend to like fly in front of telescopes and obscure the view and basically ruin a lot of the science. So for the last 10 years or so, they've been keeping track of how many filings and constellations have been proposed. And they were estimating that a total of approximately 70,000 satellites would be part of a constellation by 2030. So a bit of a discrepancy, but with the things that we are estimated at the moment, but probably a good sort of sense check as to the level of, the order of magnitude. Just a little bit more detail into the rationale that people gave on these mega constellations. I think I already mentioned it. Some experts tend to be skeptical about the market for these businesses and also the funding. So it could be possible that not all of these projects actually materialize into a reality. Again, also along the lines of ceiling on interest, it could be that these companies actually, if they don't succeed as much as expected, it could be that the numbers and not end up not actually materializing in the end, if people realize that this is not the right business case. In terms of operational and technological limitations, this is something I highlighted as well. Some people think that sort of technological solutions are going to allow us to put more objects in orbit without significantly increasing the risk, while others think that this is actually not going to happen. Also, there's the possibility of regulations coming into play and potentially putting stops to some of these projects. And some experts were kind of like confident that regulations were going to play a significant role in this. So especially when it comes to catastrophic collision events like the Iridium Cosmos. So some people highlighted that these might feel a bit like the Wild West at the moment, with many proposals coming into play. But if something goes wrong, potentially that could lead to regulators and governments imposing some limits, and these will eventually trickle down into the numbers of mega constellations that will actually happen. Whereas some people were less certain about those things and think that regulatory enforcements will likely not have much of an impact. Moving on to another question of interest. We ask experts about the orbital regions in the low Earth orbit environment. There's talk about cascading events of collisions potentially leading to the risk of collision increasing too much in these regions, to the point that operators may not be able to actually operate safely in these areas. So we ask operators whether they thought that this was a feasible scenario, something that we could actually see it happen over the next decade or so. So we broke that down into three main questions. First of all, what are the chances or the likelihood of actually the situation happening? So how likely the risk is. And then also, if this were actually to happen, what orbital altitudes would be most at risk, or where we would see the situation first unfold? Because there's a wide range of orbits that satellite operators target, and there's a big difference in how crowded some of these regions are. And then finally, for those who thought that this was a realistic situation that could actually happen, we asked them to estimate when they think this would happen. What we saw is not a very clear consensus. So there was a lot of uncertainty. Some experts even answered something like between 1 or 2% chance of this actually happening to 90% or something like that. But in general, what we found was that experts don't discount this as an unreasonable scenario. So they are aware of the risk, and they wouldn't be surprised in general if this actually materialized. So we ended up with an estimate for the equal weights decision maker between almost 0% to 70% of a chance of LEO becoming inoperable at some point in the future, with a median estimate of around 33% or so. So yeah, it's in the expert's mind, but at the moment it's not very clear whether this actually will take place or not. In terms of the regions at risk, there was a bit more consensus, and what we found approximately was that experts thought that this could happen at an altitude between 450 and 800 kilometers above the Earth, with a median estimate of around 650. And I think I've got a figure here, yes. So this figure comes from the European Space Agency report, and this highlights the number of objects in orbit as a function of altitude. So you can see that the answers that we got from experts more or less matches that region between 400 and 800 kilometers, where many of these satellites are being put. So Also to highlight that this figure looks at the number of objects, but as you increase in altitude, sort of the volume of the cell where these objects are increases. So then the density of objects per volume decreases. So actually those sort of like secondary peaks that you see above 1,000 and 1,500 would actually have lower numbers. In terms of rationale, some people actually highlighted that these might be driven by increases in insurance premiums. So if the collision risk increases sufficiently, it might not be that operators are not actually that they won't operate, but just that the insurance cover that they would need to get in order to be in those regions would be prohibitively expensive, which is an interesting way of seeing things. So it's not just about what the actual risk is in reality, but also the economics of the risk. And finally, moving on to effective mitigations, the last part of the study. What should we do about this? I just wanted to kind of highlight that consensus about the risk usually is not the same as effective mitigations. And just to give an example from climate change, I saw a study that claimed that more than 99% consensus was achieved in terms of acknowledging that climate change is mostly caused by human activities in the scientific literature. But we've seen for many decades already that this awareness about the climate change problem has not translated into effective actions. So just highlighting how the annual CO2 emissions across the world have been increasing and keep increasing even after agreements have been signed and protocols sort of promising what actions we're going to take. And there's the problem of these happening in the space debris domain as well. So we already saw the figure of how the number of objects in orbit has been increasing dramatically, and how we already have like mitigations in place, but either people don't comply with them or simply they're no longer sufficient for the context in which we're operating in. So that's kind of why we wanted to explore the effective side of mitigations and understand what could we do that actually will have a positive effect on this problem. One of the questions that we asked experts was whether they thought that mandating propulsion in orbit was a good idea. So just highlighting that over 2,300 satellites, small satellites were launched into orbit into 2022. You might think that a lot of them have propulsion when in reality, most of them are just orbiting and have no maneuvering capability. So here at the bottom left, there's a picture of Delphi Next, which was a satellite launched by the Delft University, I think around 2016 or so. And it carried a micro propulsion system that they wanted to test, which was developed by TNO. They did a handful of tests, but eventually it broke up and they couldn't really continue with the study. But there was a study in 2017 that kind of looked at the literature across all the CubeSat projects, so small satellites the size of CubeSat units, and concluded that approximately 4,000 CubeSats had been launched up to that date, and only a handful, around 10 or so projects actually carried any means of propulsion. So a lot of things in orbit, even if they're active, they don't have the capability to maneuver away from potential collisions. So one of the things that has been proposed is, okay, what if we actually force people to carry propulsion systems so that they could act in case there is a potential collision? So we ask experts to estimate whether these would have a significant impact on the collision risk. So we use collision risk as a proxy, and we ask experts what percentage of collisions in LEO do they think would be avoided by introducing propulsion. And interestingly, what we found is a dramatic lack of consensus and also very conflicting views. what we saw is that experts are not particularly uncertain when it comes to their opinion about whether this would be a useful mitigations. But instead, what we found is that experts were very much on two sides. So I highlighted kind of that gray zone of like not being really sure whether propulsion would be a useful one. And most of the experts were either on one side of the fence or the other. Some of them said that including this propulsion system would not have a significant impact, or that it would not be the best approach and would need to be combined with other mitigations, so it wouldn't have a significant impact on the risk itself. Whereas others see this as a really, really important thing that we need to be doing and mandating operators to incorporate some propulsion into their systems. And some of the rationales that they give was that if you have a collision warning between two satellites, if both of those are inactive, there's no way to actually try to maneuver around and avoid the collision. So yeah, some people think that we really need to include propulsion systems. But our results are pretty ambiguous. When we processed the data, we ended up with a fairly uninformative estimate between 0 and 95% or so for that proxy for the risk. So what we think is that in reality, we need to do more research as to what would be the impact of carrying these systems on the risk of collision. And finally, I don't know if you're familiar with this, but there's a type of mission called active debris removal, which has been attracting a lot of attention over the last decade or so. There's a handful of startups working across the globe trying to put together active debris removal missions. And these, in essence, are missions by which a satellite is launched and tries to pick up some space junk and removes it from orbit. So it's what we normally call remediation compared to mitigation. So mitigation would be making sure that once you're in orbit, you don't produce any additional debris, and making sure that you deorbit as close as quickly as possible. But sometimes satellites fail in orbit, or just rocket bodies are left without any propulsion capabilities. So kind of linking back to that image that I showed, that the space object population is going to continue increasing even if we stop doing things. People think that what we need to do is actually go up there and retrieve the trash and deorbit it. So that's where active debris removal comes into play. Although this has been in development for a few years already, it still hasn't quite matured enough to actually be demonstrated successfully. And some of the factors that affected these sort of pace of development are not just the technical challenges of designing a mission that actually finds and retrieves something in orbit, which is already quite a problem, but in principle solvable. There's many legal and political implications that are slowing down these projects, and also insurance obstacles. Mostly their dual use nature, the fact that these satellites in principle will be able to get close to satellites in orbit and grab them and potentially either tampering with them or deorbiting them and so on, raises a lot of eyebrows in the sort of military space. And there's been historical incidents of satellites from aggressive actors like getting too close in the geo belt, getting too close to other satellites and so on. So before we actually see the deployment of these missions, some of these sort of legal and political implications need to be ironed out. But what we were interested in understanding was whether experts thought that this was actually a key mitigation, or at least a useful one. So we asked them to estimate how many objects they think they must be removed per year through active debris removal to ensure the sustainability of the orbital environment. And I think I've got the answers here. Yeah. What we found is fairly a fairly good consensus when it comes to the median estimates, but kind of like long tails on the distribution. So most of the uncertainty was coming from however many we need to remove in total. And what we ended up getting was an estimate between approximately 1 object per year as the sort of the fifth percentile value, and a median estimate of around 10 objects per year, all the way up to almost 100. So in principle, if you compare this to the fact that there's thousands of space objects in orbit and there's thousands being launched every year, it seems like experts feel like ADR is not going to play a significant role. It will be necessary, and it will have some impact on the evolution of the orbital environment. But at the moment, I think there's fairly low confidence as to the significance of these mitigation. And I think that's pretty much all I wanted to mention today. Just as a summary, this is still an ongoing study. We're trying to add some experts to the pool to make sure that the data is as robust as possible, and we're still doing some post-processing of the data. We have new questions coming based on lessons learned from the first iteration of the elicitation. In terms of future work, we're quite interested in looking at the robustness of the study. So we'll be doing some sensitivity around both the calibration questions and the experts themselves. And just in terms of preliminary conclusions, we've kind of demonstrated that structure expert judgment can be a useful tool for decision making under uncertainty in the context of the space debris environment, which is something that hasn't been done before. And we managed to get some interesting preliminary findings when it comes to the future use of spacecraft and constellations, with estimates on the number of payloads being launched and also the number of objects that will be part of a constellation. We've also looked at the risk of some orbits in LEO becoming inoperable in the future, finding that although experts don't see this as an unlikely scenario, it's in the back of their minds. So it could be that it actually materializes in the near future. And we've kind of like estimated the regions at which these is most likely to take place, or the regions that are at most risk. We also looked at propulsion as a potential mitigations for the collision risk. And what we found was that there was a profound disagreement between what experts believe about propulsion. So that was an interesting thing that will require further scrutiny. And also we looked at active debris removal, which even if it were to solve all the challenges, the role that it will play, according to the experts, is going to be helpful, but definitely not essential for the mitigation of the risk in the orbital environment. So that's it for myself. Thank you for coming. And if you have any questions, please let me know.